on July 1, 2025. The Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, based in Chile, detected a faint, fast-moving object unlike anything previously seen within hours. Astronomers realized this object was on a hyperbolic trajectory, meaning it wasn't orbiting the Sun, it was simply passing through a visitor from deep interstellar space. They named it 3Ia TLAS, also designated C2025N1. The 3I meaning the third known interstellar object ever discovered. After Oumuamua, 2017 and 2, I Borisov, 2019, what makes 3I Atlas extraordinary is that it isn't just passing by. It's actively outgassing, behaving like a comet, and showing a tail before it even reached the Sun's closest point. According to early Hubble and James Webb telescope data, its nucleus may range anywhere between 0, 3 kilometers to 5-6 km, small but potent enough to carry materials older than our solar system. Itself, scientists believe it originated somewhere in the thick disk of the Milky Way. Potentially billions of years ago. Why this matters? This discovery isn't just another comet sighting, it's a cosmic time capsule. 31ATLAS contains unaltered material formed around another star system, billions of light-years away. Every dust particle, every frozen molecule inside it could hold clues about the chemistry of alien worlds. As it entered our solar system, the object began reacting to the Sun's radiation, forming jets, trails, and outgassing patterns that baffled observers. It didn't behave like any known solar system comet. That strangeness set off a wave of new observations, and when a massive solar event was detected heading in its direction, the scientific community knew something historic was about to happen. This is where the story truly ignites, because the Sun had just launched one of its most powerful CMEs of the year. And 3IATLAS was directly in its path. What is a CME and why it matters? A coronal mass ejection CME is one of the most violent events our Sun can produce, a blast of magnetized plasma and charged particles erupting from the solar corona, often traveling millions of kilometers per hour. When a CME crosses paths with a comet, it can strip its atmosphere, distort its magnetic field, or even trigger sudden outbursts of dust and gas as its surface heats and cracks open. These events can dramatically change a comet's brightness, tail direction, or even cause it to fragment. Normally, this would be a fascinating but routine solar interaction, however. This time, the target was not a normal comet, it was a rogue interstellar traveler, the predicted collision timeline. On September 19, 2025, the Sun unleashed a massive CME, recorded by both NASA's SOHO and STEREO spacecraft. Within 48 hours, modeling from NASA's Enlil Solar Propagation System projected the ejected plasma to intersect 3I Atlas S trajectory right around September 24 to 25, 2025. That means a direct CME impact was expected just as 3I Atlas was approaching its most active phase near perihelion. This was not a coincidence of timing. It was an extraordinary cosmic alignment, a deep space object billions of years old. Meeting a fresh solar eruption in real time, astronomers began preparing to watch what they called a potential activation event. When a comet or object suddenly flares up after external impact, brightening rapidly, ejecting material, or even splitting apart, it's described as activating. If 3IATLAS contained volatile materials from another star system, this CME would expose them. It could turn a dim object into a dazzling cosmic display, visible even to mid-sized telescopes on Earth. Scientists from NASA, ESA, and multiple universities coordinated to capture the moment, calling it a once-in-a-lifetime observation. And as the CME's wavefront expanded through space, all eyes turned toward 3I Atlas, waiting to see whether this ancient interstellar wanderer would flare, fragment, or awaken in ways science has never recorded before. Unusually, C-ORH coma and rapid water loss (JWST) spectroscopy shows 3IATLAS's coma is dominated by CO, with a COHO ratio far higher than almost any known comet. That means the gases streaming off this object are not what researchers usually expect. The nucleus is releasing carbon dioxide-rich plumes, even while still relatively far from the Sun. Independent ultraviolet and infrared observations, REPORT, massive water loss as well. Instruments detected water release rates comparable to a dozens of kilograms per second. At distances where normal comets are much less active, put simply, this object is expelling exotic mixes of volatiles at rates and ratios that break the usual comet template. Those gases carry a direct chemical fingerprint of the environment, where 3-1 Atlas formed, likely a different protoplanetary disk, with colder or more irradiated conditions than our own metal and dust oddities. Not a typical comet spectroscopy, and high-resolution ground telescopes have flagged anomalous metal signatures. Elevated nickel emissions and unusual trace species show up in recent analyses. Observers report polarization and tail structure that match typical dust grain behavior, including odd antitail appearances and rapidly changing fans of dust, pointing sunward at times. Those structural oddities suggest the dust grain sizes, shapes, or compositions differ from solar system comets. When you combine a C-Odich, highly active coma with rare metal emissions and weird tail morphology, you get an object whose chemistry and physical properties are fundamentally unfamiliar. That unfamiliarity matters because it changes how the object will react if something energetic, like a CME, slams into it, the CME strike scenario, and immediate effects. SolarWind models predicted a CME wavefront intersecting 3IATLAS's path during a period of peak activity. If that CME hits as forecasted, the object will experience a fast hypersur plasma shock and enhanced magnetic fields, conditions that can instantly alter a comet's environment. Expect immediate triggers, sudden brightening from exposed volatiles, rapid jet formation as pockets of ice vaporize, abrupt reorientation or disconnection of plasma dust tails, and the possibility of small fragments shedding from the nucleus. Because 3IATLAS already shows high volatile flux and unusual grain chemistry. The CME acts like a catalyst, forcing buried ESOS and rare compounds into space where telescopes can measure them. What activation means for observers and science. For observers, activation means the object could go from a faint target to an easily imaged, dynamic spectacle within hours or days, new plumes, sharp jets, sudden color changes, and tail restructuring that amateur and professional setups can capture. For scientists, activation provides fresh, unaltered samples of interstellar material in real time, the chance to measure isotopic ratios, unexpected molecules, including trace metals, and mechanical strength of an alien nucleus, even if the outcome is subtle. The data stream helps refine models of how bodies from other star systems form and break down under solar forcing. In the most dramatic case, fragmentation could eject pieces whose composition differs from the surface. Giving direct access to interior materials in every scenario, the CME plus interstellar composition combo makes this activation an unprecedented experiment in planetary science. Scientific unlocking of alien materials. If the CME strips away surface layers or forces a major outburst, telescopes and spectrometers will sample freshly exposed ices and dust that never experienced our sun. That's enormous. JWST already shows a CO-dominated coma with measurable HO and other volatiles, which means any activation will produce high-quality spectra that reveal volatile ratios, isotopic abundances, trace metals, and solid-state ice features. Those data let scientists test where 3IATLAS formed, for example, near ACO ice line in its birth disk, whether its ices were heavily processed by radiation, and how volatile budgets differ between star systems. Information you can get from meteorites or ordinary comets. This is essentially real-time chemical forensics on an object from another star, probing structure, strength, and evolution. Beyond chemistry, activation can reveal the object's physical construction. Acme shock that causes jets, shedding, or fragmentation exposes subsurface layers and tests nucleus cohesion, measuring how fast material peels off, what particle sizes dominate the ejecta, and whether interior composition differs from the surface constrains porosity, layering, and tensile strength of an alien nucleus. If fragments separate, instruments can collect spectra of interior material directly, the clearest window into primordial building. Blocks from another planetary system. Practically, this event also functions as a live drill. Observatories coordinate rapid responses, refine target of opportunity operations, and improve our multi-wavelength strategies for future interstellar visitors. In short, science and operational know-how both advance why the public cares on the cultural side. This is visceral and immediate, a cosmic messenger formed around another star, reacting to our sun's fury and captured on camera. That narrative powers engagement. Schools, live streams, amateur astronomers, and news outlets all participate. It's not just data. It's a shared spectacle that drives interest in space science and funds future missions, whether the activation is subtle or spectacular. The event highlights how dynamic and interconnected the galaxy is, and it gives people a front-row seat to a real scientific investigation that could reshape our ideas about planet formation and the materials that cross between stars. Observable signs. What you'll see if activation occurs: look for clear, fast changes. A sharp, brightening magnitude jump over hours to days. Sudden jets or fans appearing in the coma. Rapid tail reconfiguration or disconnection events. Color shifts in the coma from different gases, dust, and small fragments, detaching and moving away. Professional observatories, JWST-H, STCAC, Gemini Plus coordinated amateur networks, and live telescope feeds increase the chance of catching these behaviors in near real time. Spectroscopy alerts will show changes in COHO, CO lines, and any unexpected metal signatures. Those spectral shifts are the first hard evidence of newly exposed material. Keep an eye on observatory feeds and social astronomy channels for image stacks and spectra releases for main scenarios. And their meaning: major outburst. A bright, rapid eruption ejects large amounts of dust and gas. This is the richest scientific payoff. Clean spectra and dramatic imaging. Moderate response. Increased activity within cometary norms. Still valuable for tracking trends in volatile release and dust dynamics. Minimal effect. The CME dissipates, or the nucleus buffers the shock, telling result about surface insulation and structural resilience. Fragmentation. Parts of the nucleus break off, exposing pristine interiors. Rare. But the best possible direct sample of alien material. Each outcome teaches something different. Chemistry, mechanical properties, or resilience. None is amiss. Even a quiet response tightens constraints and improves models for interstellar bodies and solar wind interactions. How to follow in real time. Bookmark official feeds. NASA, ESA, JWST updates. Follow Watchers News and Space.com for timely analyses, and check virtual telescope live streams. Many observatories post near-real images within hours. If you're an amateur imager, try stacking short exposures and post to astronomy communities. The crowd often spots transient jets or fragments first. Above all, expect rapid updates. This is a live science event, and the situation can evolve on hour-long timescales. Interstellar object meets solar storm. Events like this are nearly unheard of. Interstellar objects themselves are rare. Only 3 have ever been confirmed in history. 1I Oumuamua, 2I Borisov, and now 3I Atlas. But this is the first time one has coincided with a major coronal mass ejection heading directly into its path for astronomers. That means an extraordinary chance to observe how a foreign object, forged under an alien sun, responds to the fury of ours. It's like watching 2 different worlds collide. The physics of how plasma, magnetic fields, and ionized gas interact with an interstellar nucleus has never been observed before. This is pure first-hand discovery happening live, once-in-a-lifetime experiment for humanity because of its speed and trajectory. 31ATLAS will soon exit the solar system forever. Moving out toward interstellar space again, scientists won't get a second chance. The CME's collision, therefore, is essentially a one-time natural experiment. One we didn't plan, but one the universe arranged for us. Every telescope currently pointed at JWST, Hubble, Gemini South, and multiple Mars orbiters is working in coordination to capture every spectrum and image possible. If the object flares up or fragments, the light patterns could even reveal internal layering and volatile storage that tell us about the formation of other star systems. Think about that. We could be studying the geological fingerprints of an alien solar nursery, right here in our backyard. Why scientists call it activation. The term activation sequence, ESNT, science fictionate, comet science, shorthand for a cascade of changes caused by external energy input as the CME hits. Magnetic pressure and shock waves can crack sealed volatile pockets, leading to a chain reaction of sublimation, venting, and ejection. For 3I Atlas, this could mean a rapid increase in brightness, sudden outgassing jets, or even electrical discharges as magnetic fields reconnect around the body. For scientists, it's a data goldmine. For the public, it's a visual event we might actually witness in the coming weeks. What comes after the impact, after the CME hit? Telescopes will continue monitoring for at least 6 months. The key measurements will be light curves, spectral changes, and coma dynamics, if 3I Atlas shows sustained brightening. That suggests it entered a new active phase, meaning the CME didn't just trigger surface ejection but expose deeper volatile rich layers if the light output drops quickly. It may mean a short-lived flare or a surface blow-off event. ESA's Mars orbiters, located near the object's trajectory, are also tracking post-impact plasma readings to see if the comet's ion tail interacts with solar magnetic flux in unusual ways. This combination of data, optical, infrared, and plasma could finally tell us what these objects are made of and how stable they are when bombarded by a star's energy. Why the public should stay tuned. This isn't just another space headline, it's the first controlled cosmic interaction between two star systems, materials, ours and another's, every time telescopes detect a molecule, a dust composition, or a plasma reaction. It's effectively the first contact between our solar science and alien matter. You're witnessing history unfold in real time, a cosmic experiment, billions of years in the making. As more data arrives, NASA and ESA will likely release composite imagery showing the CME front impacting 3I Atlas and its aftermath. Whether it becomes a dramatic visual spectacle or a quiet scientific milestone, the takeaway remains the same. Our sun just touched a messenger from another world, and the results could reshape everything we thought we knew about interstellar travel material, exchange, and the life cycle of cosmic matter. So stay alert for updates. The activation may have already begun, and the data that follows could be the first proof that the building blocks of other star systems are not so different from our own.